Welcome to our quiet exploration of Earth's deep history. Tonight, we're diving into geology, the story written in our planet's very structure. It's a tale told in stone, a silent record stretching back billions of years. Long before maps existed, or people named the stars, this world was already in motion. It changed itself constantly, without a sound. Towering mountains grew, then slowly crumbled away. Oceans appeared, then dried up, only to return much later. Continents wandered across vast seas of molten rock, shifting their positions over immense stretches of time. The ground beneath you right now feels solid, unchanging, but it is unimaginably old. And yet, it's still alive, still shifting, still transforming. This is geology. It's about fire and water, about creation and destruction, about a kind of beauty that takes millions of years to truly unfold. With every step you take, within every small stone, there are quiet echoes of long-gone volcanoes, massive ice sheets, and distant stars. We will trace these whispers now, as we begin our journey. First, let's consider Earth's outer shell. The planet's crust is much thinner than you might think. Imagine scaling down our entire world to the size of a common apple. The hard, outer layer where we live, the continents and ocean floors, would then be no thicker than the skin of that fruit. This seems almost impossible, doesn't it? A colossal globe, supporting everything we know, resting on such a delicate surface. But it is absolutely that outer shell, the crust, is incredibly thin. On land, under the continents, it generally goes down about 30 kilometers. Out in the oceans, it's even less, often under 10 kilometers deep. Think about that for a moment. All the vastness of the land, all the deep ocean trenches, everything we've ever built, everything we see, rests on this fragile layer. Beneath that thin skin lies the mantle. This is a huge part of Earth's interior, a vast region of rock that isn't quite solid, but flows extremely slowly. It makes up the majority of our planet's volume and mass. The crust, with all its continents and ocean floors, basically floats on this slowly moving mantle. It's like enormous, rigid rafts drifting on incredibly sluggish, molten currents. These deep currents are what drive plate tectonics, constantly carrying and reshaping the surface. So, when you look at towering mountains, wide valleys, or even the deepest ocean trenches, they're really just tiny wrinkles. They're ripples on the surface of an enormous, almost perfectly spherical stone. Everything we recognize, every forest, every city, every drop of every ocean, exists right on top of this layer, which is so thin it almost disappears when you consider the planet's immense scale. It's a humbling thought how delicate our world's surface truly is. Now, let's talk about granite. This incredibly common rock, which forms the heart of so many mountain ranges, wasn't always the solid, rugged material we see today. Long ago, deep underground, it flowed like molten rivers. It was alive with intense heat. Far down within the Earth's crust, molten rock, called magma, collected in hidden chambers. It moved slowly, ponderously, like fiery rivers beneath the surface. Over millions of years, this magma gradually cooled. And as it cooled, it crystallized, slowly solidifying into the familiar, speckled rock we now know as granite. Every single grain you see in granite, each bit of quartz and feldspar, once shimmered and swirled in that molten, glowing state. Then, over aeons, it solidified, becoming fixed in time. When you reach out and touch a piece of granite, whether it's a countertop or a mountain face, you're actually touching the cooled remains of that ancient, fiery flow. It's a moment from deep time, frozen forever. Many of the world's most famous landscapes, like the dramatic cliffs of Yosemite or the rugged beauty of the Scottish Highlands, were carved from granite that rose and solidified far below the surface. This stone holds the very patience of the planet within it. It's a quiet reminder that what appears utterly solid and unmoving today was once a liquid light, slowly changing under immense pressure, eventually becoming something incredibly enduring and timeless. Next, consider diamonds. Most diamonds take billions of years to form deep within the mantle. They're born from carbon, subjected to crushing pressure and incredible heat, far beyond what we can easily imagine. But nature can be full of surprises. Under the most extreme, sudden conditions, carbon can transform into diamond almost instantly. These rapid transformations happen many miles beneath the surface, where temperatures are hotter than molten metal, and pressures are so intense that humans can't replicate them for very long. When volcanic eruptions eventually bring these precious gems to the surface, they travel upward through narrow, carrot-shaped pipes of rock. These formations are called kimberlites. Each diamond, whether it formed slowly over eons or in a geological blink, carries a story from the very depths of Earth's creation. Every diamond you've ever seen, no matter how tiny, once existed in a place of darkness and heat so fierce that it could melt steel in an instant. Whether their creation was a slow, patient process or a quick, explosive event, each crystal is a perfect record of transformation. They are born from chaos and immense pressure, then slowly rise towards the light, carried through the very bones of the planet itself. Mountains, those symbols of permanence, are actually still very much alive with movement. Some mountains are rising faster than your fingernails grow. While they seem eternal and unmoving, deep beneath the surface, the Earth's tectonic plates are constantly pushing and colliding. This immense force slowly shoves rock upward, inch by inch, in places like the Himalayas and parts of the Andes. This slow, relentless collision is still lifting peaks at a rate that's faster than your fingernails lengthen. What feels utterly solid beneath our feet is actually part of an endless cycle of uplift and erosion. Wind, water, and ice are constantly working to tear mountains down, grain by tiny grain. At the same time, powerful forces deep below are rebuilding them. This rhythm has played out for hundreds of millions of years. A mountain might seem completely motionless, but if you could speed up time, you would see it literally breathe. You would witness it swelling upward as continents slowly collide. The very stone you stand on could once have been part of the ocean floor, carried skyward over vast periods of time. These colossal giants serve as a powerful reminder that our planet is not still at all. It's in constant motion, reshaping itself even as we sleep. In fact, entire continents float like enormous rafts on molten rock. The ground we stand on is actually drifting over a hidden, deep sea of molten material. Below the crust, as we discussed, is the mantle. This region is so incredibly hot that solid rock acts like an unbelievably slow, moving liquid. The continents, these enormous, rigid slabs of stone, rest on this mantle. They drift across it through immense spans of time. They slide against each other, they collide, and they separate, all at speeds of only a few centimeters each year. But over millions of years, these tiny movements add up. They completely reshape the world. Oceans open up, and then they slowly close. Huge mountain ranges rise, and entire climates transform. The continents we recognize today are travelers, always in motion, even though their journey is completely invisible to us. This slow drifting is what once brought all the land together into a single, massive supercontinent called Pangaea. And one day, far in the future, it will bring the continents together again. Our planet is truly alive beneath its seemingly calm surface, and we are all passengers on its vast, drifting plates. We are carried across these geological seas without ever feeling the motion. Earth's surface is constantly recycling itself through a process called plate tectonics. Nothing on the planet's surface is truly permanent. The continents and ocean floors that we see today are all part of an endless process of destruction and renewal. It's a cycle known as plate tectonics. Where these massive plates collide, towering mountains are forced upward. Where they pull apart, New ocean crust forms as molten rock from deep within the Earth wells up to the surface. In other places, one plate dives beneath another, sinking back into the mantle, where it melts and becomes part of the Earth's interior once more. Even the ground beneath the oceans is born, spreads outward from its point of origin, and then eventually disappears. This entire process unfolds on a timescale of tens of millions of years. This is a fleeting moment in Earth's incredibly long history. Every single grain of sand, every towering cliff, every vast volcanic plain is part of this huge planetary cycle. Earth is the only world we know of that recycles itself so completely. It uses the slow, immense power of heat and gravity to keep its surface perpetually young. The planet's skin is never truly still. It's forever shedding and remaking itself in a quiet, graceful, and ceaseless motion. The Himalayas, those majestic peaks, are still growing taller every single year. High above the clouds, these colossal mountains continue their ascent. Their growth started around 50 million years ago, when the Indian plate, carrying the subcontinent, began to collide with the Eurasian plate. This immense collision crumpled the Earth's crust like a piece of fabric being folded. That collision is still happening right now. It's pushing the mountains upward by a few millimeters each year. The peaks might look timeless and unchanging, but their summits are steadily climbing towards the sky, even as wind and glaciers are constantly carving them down, grain by grain. Every small tremor in that region, every deep earthquake, is a quiet whisper of that immense pressure still at work below. These mountains aren't just ancient relics of the past. They're the living result of an ongoing collision, a process that began long before humans ever existed. The same collision that built the highest peak, Everest, continues to reshape the land beneath millions of people. In their silent, continuous rise, the Himalayas remind us that Earth's power is incredibly patient, utterly relentless, and always in motion. It sculpts entire continents as easily as a sculptor might work with clay. Continents actually drift as fast as your hair grows. If you were to precisely measure the movement of a continent, you would find that it advances at about the same speed your hair lengthens in a month. It's a tiny, almost imperceptible pace. Yet, over geological timescales, that small, consistent movement completely reshapes the entire face of the planet. Continents slide on top of the Earth's mantle, carried along by vast convection currents deep within our world. The Atlantic Ocean, for example, grows a little wider every single year, while the Pacific Ocean slowly shrinks. In millions of years, the maps we recognize today will be unrecognizable. Africa will inch closer to Europe. Australia will continue to move north, and eventually, the continents may merge again into a single, colossal landmass. This slow, steady drift connects the fossils of ancient creatures found on continents now separated by vast oceans. It also explains why mountain ranges on completely separate continents often share the same geological origins and structures. The ground beneath our feet feels utterly solid and unmoving, but it is actually part of a grand, restless voyage, a journey that has never stopped since the planet itself was born. The ocean floor, surprisingly, is much younger than most of the continents. Beneath the waves, there's a hidden world that's in constant renewal. While the ancient cores of continents hold rocks that are billions of years old, the seafloor is remarkably young. Along the mid-ocean ridges, molten rock rises up, cools, and forms brand new crust. This new crust then slowly spreads outward from the ridge. As it drifts away, it eventually sinks back into the mantle at deep ocean trenches, where one tectonic plate slides beneath another. This continuous recycling means that no ocean crust lasts longer than about 200 million years. That's a mere fleeting moment in Earth's incredibly long history. The continents, by contrast, are ancient survivors. They've floated above this cycle of destruction and renewal for much longer. If you could somehow watch the planet's surface over vast stretches of time, you would see the oceans form and then vanish, like the slow, rhythmic breath of a colossal being. The seafloor is like the planet's heartbeat, constantly renewing itself endlessly. It's a powerful reminder that even the deepest, darkest places on Earth are alive with motion and profound change. Hidden across the vast plains of the ocean floor, the rocks are patterned like a giant barcode. These alternating magnetic stripes mark times when Earth's magnetic field completely reversed its direction. North and south literally swapped places. As new crust forms along the mid-ocean ridges, tiny minerals within the molten lava align themselves with the planet's magnetic field, just like invisible compass needles. Once the lava cools and hardens, that magnetic direction is locked in forever. Millions of years later, another reversal happens, and the next band of newly formed rock points in the opposite direction. By carefully studying and reading these stripes, scientists can trace the entire history of magnetic flips, stretching back tens of millions of years. This incredible discovery was one of the most important keys that helped prove the theory of plate tectonics. It showed, definitively, how the seafloor spreads outward over immense periods of time. So, beneath the oceans lies not chaos, but a perfectly ordered record of the planet's invisible forces. It's a story written in stone, powered by magnetism, heat, and the slow, steady pulse of geological time. When molten rock cools on the surface of the Earth, something truly extraordinary occurs. Tiny particles of iron and nickel, embedded within the rock, align themselves with the planet's magnetic field. They act like countless microscopic compass needles, all pointing in the same direction. Once the lava cools and completely hardens into solid rock, those magnetic directions are permanently locked in. This preserves a perfect record of the magnetic field's orientation at that exact moment in time. Scientists meticulously study these natural magnets to map the shifting history of the Earth's poles. Every reversal, every gradual wandering movement of magnetic north is captured within the stone. It's frozen there as the planet's molten skin solidifies. These magnetic fingerprints are a crucial part of how geologists definitively proved that continents drift and seafloors spread. In every volcanic rock, there lies a silent record of Earth's magnetic pulse, whispering clues about ancient directions and the powerful, invisible forces that shape the space around our world. The planet's memory is magnetic, a story written in the iron heart of stone. Every single volcano on Earth is connected to a hidden magma chamber far below the surface. Each volcano has a beating heart of molten fire. These underground chambers are vast reservoirs of liquid rock, called magma. They feed eruptions that can reshape entire landscapes and even change global climates. Some of these chambers are relatively small and shallow, while others are immense and incredibly deep, reaching far beneath the Earth's crust. Inside them, crystals slowly form, gases rise, and pressure steadily builds. This continues until the solid rock above can no longer contain it. Then, with staggering power, the chamber vents its fury through cracks and openings, pouring lava and ash across the world above. Between eruptions, these reservoirs remain hidden, slowly refilling and evolving, preparing for their next release. Modern technology allows scientists to glimpse their shapes, using seismic waves much like an ultrasound scan for the Earth. Each volcano is part of this deep, breathing network, a powerful reminder that beneath calm fields and seemingly sleeping mountains, there are vast, glowing worlds of molten stone waiting quietly below. Not all volcanic eruptions are sudden, explosive moments in time. Some are incredibly patient and relentless, flowing for ages beyond our imagination. When massive plumes of molten material from the mantle are released, the result can be a flood basalt. This is a vast outpouring of lava that can continue for hundreds of thousands of years. These enormous eruptions can bury entire regions beneath miles of solid rock. The Deccan Traps in India and the Siberian Traps in Russia are enormous relics of such ancient fire. During their long reign, they released enough gas and heat to drastically alter the planet's climate and change the very course of life itself. Standing on one of these hardened lava plains today, it's almost impossible to imagine the molten rivers that once stretched to every horizon. They remind us that sometimes Earth reshapes itself not with sudden explosions, but with the slow, unstoppable rhythm of fire, spreading endlessly beneath the open sky. If you could walk across the very bottom of the sea, every single step you took would land on basalt. This is a dark, heavy rock born of fire. It forms when molten material from the mantle erupts along mid-ocean ridges and then cools incredibly quickly as it comes into contact with cold seawater. The result is a vast, unbroken crust, stretching across the ocean basins like the planet's own armor. Unlike the lighter rocks that make up the continents, basalt is rich in iron and magnesium, which gives it its deep, dark color and its significant weight. Its solid layers are continually renewed as the seafloor slowly spreads outward, while older sections sink back into the mantle and melt again. Every square inch of the ocean floor has been part of this endless cycle of creation and destruction. Beneath the waves, basalt holds the history of Earth's most patient movements. Layer upon layer of cooled magma forms the quiet, dark foundation of the world's oceans. When lava erupts beneath the ocean, it cools so rapidly that its outer layer hardens almost instantly. Meanwhile, molten rock from within continues to push outwards. This strange process creates rounded shapes that look like pillows or bubbles, stacked one upon another. These smooth, bulbous formations, appropriately called pillow lava, can cover entire stretches of the seafloor. Each pillow is a snapshot of fiery motion, frozen in an instant. It clearly shows how molten rock reacts dramatically with cold seawater. When explorers discover pillow lava on land, it's a clear indication that the area was once deep underwater. The sight of it is both eerie and beautiful, as though the stone itself still remembers flowing like a liquid before being sealed by the chill of the sea. These shapes are truly geological sculptures of time, proof that even in the dark, crushing depths, the planet's creative forces are always alive and actively at work. In moments of explosive volcanic eruption, lava can cool so incredibly fast that crystals don't even have time to form at all. The result is obsidian, a natural glass that gleams with a dark, striking beauty. It is smooth, incredibly sharp, and highly reflective. It forms when molten rock meets cold air or water and solidifies almost instantly. For thousands of years, humans have highly valued it for its perfectly sharp edges, crafting blades, tools, and intricate ornaments from it. Yet, behind its mirror, like surface lies a story of extreme, sudden change. Its molten fire arrested mid-motion, immense heat transformed into fragility. Obsidian breaks easily, but along the break, it reveals stunning, curved patterns called conchoidal fractures. It's as if each fracture remembers the original flow of the lava. This dark, glassy rock stands as one of geology's most dramatic contrasts. It's born in violence, yet perfectly still. It's fragile yet ageless. It's a piece of fire caught forever in the stillness of stone. Sometimes, the smallest traces of the past are preserved within rocks, trapped within the tiniest hollows of ancient stone. Scientists have found microscopic bubbles of air that have survived for millions of years. These preserved pockets are like perfect time capsules. They seal the precise chemical signature of the atmosphere from ages long past. By carefully studying them, researchers can learn exactly what gases once filled the skies of our ancient planet. They can determine how much oxygen existed, how much carbon dioxide warmed the Earth, and how volcanic activity, or even early life itself, changed that delicate balance. Some of these precious bubbles formed in cooling lava, others within ancient sediments or even in old ice. Each one holds an echo of an ancient breath, a ghost of the air that once surrounded early forests, colossal reptiles, or even the very first life to breathe on this planet. To hold such a rock in your hand is to hold a fragment of a vanished sky, a delicate, irreplaceable record of the ever-changing air that connects all living things across the long, slow history of Earth. Far below the surface of the oceans, there are mountain ranges that absolutely dwarf the world's highest peaks. Along the mid-ocean ridges, immense chains of volcanic mountains stretch for tens of thousands of miles. They rise higher from their base on the seafloor to their crest than Mount Everest does above sea level. These submarine ranges are mostly unseen by human eyes, shrouded in perpetual darkness and immense pressure. Yet, they are among the most geologically active regions on Earth. Lava continually emerges from cracks and fissures, steadily building new peaks and valleys in a slow, constant motion. The tallest of these hidden giants, such as Mauna Kea in Hawaii, when measured from its true base deep beneath the sea, surpasses even the great Himalayan summits. They are powerful reminders that much of Earth's beauty and grandeur lies unseen beneath the waves. They are vast, silent kingdoms of rock that grow and shift in darkness, quietly shaping the world from below, without ever catching a single glimpse of the sun. At the very heart of the Pacific Ocean lies the Mariana Trench. This is a chasm so incredibly deep that if Mount Everest, the world's highest peak, were dropped into it, its summit would still be submerged by more than a mile of water. The trench's deepest known point, the Challenger Deep, reaches nearly 7 miles beneath the surface. That's almost the same distance that passenger planes travel above the Earth. Down in that crushing darkness, the pressure is immense, powerful enough to flatten solid steel. Yet, even in that extreme environment, life endures. Strange, glowing organisms thrive in the black water, living among mineral-rich sediments. The trench itself marks a subduction zone, a place where one tectonic plate slips beneath another and sinks back into the mantle. It's not just the lowest point on Earth, but one of the planet's great engines of renewal. It reminds us how tiny the visible world is compared to the vastness that remains hidden below. Even when the ground seems completely still, it is actually vibrating with the faint murmurs of constant motion. Across the planet, thousands of tiny earthquakes ripple through the Earth's crust every single day. They are too small for humans to feel or even detect without special equipment. These micro-earthquakes release little bursts of energy as the Earth slowly adjusts to stresses deep below its surface. Scientists use incredibly sensitive instruments to record these whispers, creating detailed maps of shifting fault lines and hidden magma flows. Together, these tiny tremors form a background hum that never ceases. It's the quiet, persistent pulse of a living planet. This ceaseless trembling tells geologists where faults are slowly creeping, where pressure is subtly building, and where volcanic systems are quietly stirring. The stillness of the world is, in many ways, an illusion. Beneath every mountain, forest, and sea, the planet moves in countless small ways, sighing, cracking, and settling in slow, secret rhythms that carry the story of Earth's restless, active heart. Sometimes, when the ground shakes with enough force, the entire landscape itself can change direction. During exceptionally powerful earthquakes, the land can tilt or shift so abruptly that rivers are actually forced to reverse their flow. This rare, astonishing phenomenon has been recorded in events like the Great New Madrid earthquakes of the early 19th century, when sections of the mighty Mississippi River temporarily flowed upstream. The sudden movement of the Earth's crust can raise one side of a fault or drop another, creating natural dams or lowering valleys. For a brief, incredible moment, the sheer power of Earth's internal forces can overcome the steady pull of gravity that guides every single drop of water. When balance eventually returns, the rivers often carve new paths through the changed terrain. These moments reveal the immense strength of geological motion, showing that even something as constant and ancient as a river can be turned backward by the planet's deep, hidden forces. Not all tectonic motion announces itself with dramatic earthquakes or visible destruction. Along certain sections of faults, the Earth's crust slides so slowly and evenly that there is no noticeable shaking at the surface at all. This quiet, continuous movement is known as fault creep. It relieves pressure in small, continuous increments rather than in sudden, violent bursts. It's completely invisible to anyone standing above ground, but it's measurable through highly sensitive instruments that can detect motion of just a few millimeters per year. Some faults in California and Turkey move this way, gliding smoothly while neighboring sections remain locked and tense, building up pressure. These creeping portions may actually prevent larger earthquakes from forming in those specific regions, yet they can also transfer stress elsewhere along the fault line. This subtle, silent dance between tension and release is part of the planet's constant balancing act. Even without drama or noise, the ground beneath us is shifting, whispering in slow motion as the Earth adjusts itself, grain by patient grain, across the ages. At the very center of our planet lies a sphere of molten and solid metal, under pressures that defy comprehension. The temperatures there reach more than 9,000 degrees Fahrenheit, rivaling and even exceeding the visible surface of the Sun. This immense heat is leftover energy from Earth's formation, combined with the constant decay of radioactive elements deep inside. Though we will never see it directly, this core drives everything from volcanic eruptions to the powerful magnetic field that shields all life on Earth from harmful cosmic radiation. Its motion churns like a colossal dynamo, generating invisible lines of force that extend far into space. The inner core, a solid sphere of iron, rotates slightly faster than the planet above it, while the outer layer flows in a liquid form. This hidden furnace is the beating heart of the Earth, the ultimate power source that keeps our world alive with constant movement, warmth, and quiet resilience. There might even be an entire ocean hidden deep inside the mantle. Far beneath the Earth's crust, where rock glows with intense heat and pressure, scientists have discovered minerals that contain vast amounts of trapped water. These discoveries suggest that an entire ocean's worth of water, possibly even more, may exist hundreds of miles below the surface. This water is bound within crystal structures rather than flowing freely like an underground sea. If this hidden reservoir were ever released, it could fill the world's surface oceans multiple times over. It's not an ocean in the familiar sense, but rather a deep, ancient secret storage of the very substance that sustains all life on our planet. The slow movement of tectonic plates may carry water downward into this deep realm, only for it to eventually return to the surface through volcanic eruptions and rising plumes of molten rock. This unseen cycle could be one of the crucial keys to understanding why Earth has oceans at all. Even in the deepest stone, water finds a way to endure, waiting patiently inside the planet's mantle for eons. Underground caves can host crystals that grow larger than a person. In the quiet, humid darkness beneath the deserts of northern Mexico, there lies a breathtaking cathedral of crystal. This is the Cave of the Crystals, buried deep within a silver mine. It holds translucent gypsum blades that stretch more than 30 feet long. Each one took hundreds of thousands of years to grow in perfect stillness, nourished by hot, mineral-rich water that once completely filled the chamber. When the water eventually drained away, the colossal crystals remained, gleaming like frozen moonlight in the humid air. Entering this cave is like stepping into another world entirely. one built not of rough rock and fiery magma, but of slow, delicate, almost impossible perfection. The precise conditions required to create such formations are almost impossibly rare. It's a delicate balance between consistent heat, mineral saturation, and immense spans of time. These enormous crystals remind us that even the hardest materials on Earth can move and change, given enough patience. They are the planet's most beautiful expression of stillness, shaped by time itself. Giant gypsum crystals shimmer in Mexico's Cave of the Crystals. Deep below the surface, where the heat and humidity are so extreme they can melt scientific equipment in minutes, lies one of the most breathtaking sights ever discovered. Miners found the Cave of the Crystals in the year 2000. It contains gypsum formations so massive they resemble towering pillars of light. Some of these crystals weigh dozens of tons and stretch across the chamber like colossal, clear glass beams. The crystals formed because mineral, rich groundwater remained at an incredibly steady temperature for hundreds of thousands of years. This allowed molecules to arrange themselves with perfect, slow symmetry. When the cave was finally drained, the growth of the crystals stopped, freezing the scene forever. The atmosphere inside is so hot and thick that no one can stay inside for long. Yet, for brief moments, explorers have walked among these shining walls of translucent stone. It is a vision of pure geological art, created not by human hands, but by time, water, and the quiet, patient chemistry of the Earth itself. Salt domes can actually pierce through solid rock like slow, motion explosions. In regions where thick layers of ancient salt lie buried deep beneath heavier, overlying rock, a strange and powerful phenomenon can occur. Over millions of years, the salt slowly begins to flow upward. It's pushed by immense pressure from the surrounding layers. Although salt seems solid, it behaves like an incredibly viscous fluid when under great stress over long periods. It rises through the rock above it, bending and breaking the layers, creating massive, dome-shaped structures that can reach miles in height. These salt domes sometimes trap oil and natural gas, forming reservoirs that have shaped entire industries and economies. From the surface, they might appear as gentle swells in the landscape, but beneath the ground, they are vast, silent pillars of slow, powerful movement, actively reshaping the Earth. Each one tells a story of ancient seas that evaporated long, long ago, leaving behind minerals that continue their quiet, relentless climb skyward. It's proof that even solid ground is capable of flowing like a patient, unstoppable tide. What looks like a fallen tree that has simply turned to stone is actually something far stranger and more delicate. Petrified wood is literally quartz, atom by atom. When a tree is buried by volcanic ash or sediment, minerals carried by groundwater slowly seep into its cells. Over thousands of years, each tiny structure of the wood is replaced, molecule by molecule, with quartz. This incredible process preserves every single growth ring, every knot, and every fiber in perfect, astonishing detail. The result is a fossil that still looks exactly like wood, but feels cold and heavy to the touch. Sometimes, trace elements color it in beautiful hues of red, yellow, or green, painting a natural artwork within its grain. Holding a piece of petrified wood is like holding a memory made solid. It's a living thing transformed into crystal by the immense patience of time. It is nature's quiet way of telling us that nothing truly disappears. It only changes form, keeping the story of life locked within stone. Coal began as ancient forests, trapped in vast, swampy worlds. Long before humans ever walked the earth, vast tropical forests covered much of the land. When these forests died, their fallen trunks and leaves sank into oxygen-poor swamps, where decay slowed to an almost imperceptible crawl. Layer upon layer of plant matter slowly built up, pressing down under its own immense weight. Over millions of years, immense heat and pressure transformed that buried organic material into coal. This is a dense rock made almost entirely of concentrated carbon. Within every piece of coal lies the energy of sunlight, captured by plants from a prehistoric sky. Burning coal releases that ancient sunlight once more, a ghostly return of energy stored for eons. The process that created it tells a powerful story of transformation, where life became stone and sunlight became fuel. Every lump of coal carries the silent imprint of ancient forests, the very breath of a vanished world, condensed into dark, glittering veins beneath our modern one. Oil, that vital resource, comes from the buried remains of ancient plankton. Long before even the dinosaurs roamed the land, the Earth's oceans were teeming with microscopic life. When those tiny organisms died, they sank to the seafloor and mixed with mud, forming thick layers of organic sediment. Over millions of years, the immense weight of the ocean pressed them deeper and deeper, heating and compressing them until their carbon-rich remains transformed into liquid hydrocarbons. Trapped within porous rock, these ancient molecules became the oil that powers modern civilization. Every single drop of oil we burn once drifted through a primordial sea, gathering sunlight through the simplest forms of life. In a way, the energy that fuels our world is the sunlight of Earth's deep past, stored beneath miles of stone. The story of oil is not only one of geology, but of biology, chemistry, and time, all woven together in the quiet darkness below the surface, waiting patiently for discovery. Every single grain of sand tells the story of a vanished mountain. Each tiny grain you find on a beach or in a desert once belonged to something far, far greater. Long before it came to rest in its current location, it was part of a towering mountain or an ancient bedrock plain. Over millions of years, wind, water, and ice patiently ground that rock down into its smallest possible pieces, carrying them across rivers and seas. A single grain might have tumbled through massive glaciers, flowed down deep canyons, or drifted across vast oceans before finally coming to rest. Under a microscope, its unique shape and composition can reveal the kind of rock it came from and the incredible journey it took. Some grains still shine with tiny fragments of quartz from ancient continents. Others are volcanic shards from fiery eruptions long past. Every handful of sand is a storybook of time, a collection of broken worlds, reduced to glittering fragments that will one day be pressed back into solid stone and begin the cycle all over again. In a few rare deserts around the world, the shifting of sand dunes creates a deep, resonant hum that can last for minutes. These are known as singing dunes, found in places like Morocco, Chile, and the Arabian Peninsula. They produce notes so pure and deep they can sound like the very voice of the earth itself. The sound comes from countless grains of sand sliding and colliding in unison, vibrating at a frequency somewhere between the deep tone of a cello and a low, rumbling roar. Scientists believe that the sand grains must be nearly uniform in size and perfectly dry for this unusual effect to occur. Travelers describe the experience as haunting, as though the dunes are breathing or even speaking. Ancient peoples often regarded these sounds as mystical, believing they came from hidden spirits or the gods of the desert. In truth, it is a fascinating interplay of physics and friction, working together, turning the landscape itself into a natural instrument that sings the slow, patient music of the shifting earth. Along certain coastlines, the sand beneath your feet wasn't carved from stone at all. Instead, it was built by life itself. Over centuries, the shells of countless tiny marine creatures, such as mollusks and foraminifera, have broken down into fragments so fine they resemble powdered ivory. These biological sands can gleam brilliant white under the sun, shimmer pink from crushed coral, or even glow golden from the remains of microscopic algae. Each grain is a tiny fragment of something that once lived, a piece of the ocean's past returned to the shore. Walking along such a beach, is like stepping through the ruins of invisible kingdoms, where waves and tides have turned the intricate architecture of life into a soft, constantly shifting tapestry. The world's most famous white beaches, like those in the Bahamas and the Maldives, are living evidence that time and biology can build beauty as surely as rock and fire. Not all beaches shimmer with predictable gold or white colors. Some are dramatically black, formed from cooled lava. Others are green, from rare olivine crystals. Some are strikingly pink from crushed coral, or deep red from eroded volcanic rock. Each color tells a unique geological story about its source material and the powerful forces that shaped it. Black sands often line volcanic islands, formed when molten lava met the sea and shattered into countless tiny, glassy fragments. Green beaches appear where rare minerals from deep within the mantle are washed ashore. Pink hues come from crushed shells and coral mixed with white sand, while red sands are tinted by iron, rich rock that has oxidized over vast stretches of time. Walking these colorful shores is like wandering through the natural palette of the planet itself. Every wave rearranges grains that carry the memory of fire, water, and time, blending the world's elemental forces into natural art that shifts and glows beneath the ever-changing light of the sky. Glaciers might appear still and unmoving, yet they flow like slow, immense rivers of rock. Over centuries, the immense weight of accumulated snow compresses into incredibly dense ice. This ice then slowly slides downhill, reshaping everything in its path. These frozen rivers grind against the mountains, scraping out vast valleys, polishing stones smooth, and carrying enormous amounts of debris for miles and miles. When they eventually retreat, they leave behind wide, U-shaped valleys, scattered boulders, and shimmering lakes that fill their abandoned paths. The distinctive fingerprints of glaciers can be found on nearly every continent, from the smooth granite domes of Yosemite to the deeply carved fjords of Norway. Even now, glaciers continue their patient, relentless work, grinding ancient rock into fine dust that then drifts on the wind. They are true sculptors of continents, artists of time and temperature, shaping the land, grain by tiny grain. In their quiet persistence lies a powerful reminder of the planet's delicate balance, where even the coldest forces flow with a power strong enough to change the entire world. Although glaciers usually creep at the incredibly slow pace of mere inches per day, a few flow so quickly that their shifting can actually be observed within a single afternoon. These fast, moving rivers of ice are known as surge glaciers. They surge forward when meltwater lubricates the ground beneath them, drastically reducing friction and allowing massive sheets of ice to slide rapidly forward. In Greenland and parts of Alaska, scientists have documented glaciers racing ahead at surprising speeds, their fractured surfaces groaning and cracking loudly as they go. From a distance, the motion seems impossible, solid ice behaving like a liquid stone. Yet, this movement carries enormous power, reshaping valleys and transporting rock by the ton. As they surge, they also remind us that even in their frozen stillness, glaciers are very much alive with motion. To witness one in movement is to see time itself accelerate, the slow, patient rhythm of the earth condensed into a visible, breathtaking surge. Beneath the surface of a glacier, where the pressure is immense and temperatures hover just below freezing, ice stops behaving like a solid. Instead, it flows. Not quickly, but slowly and continuously, folding and bending like thick honey poured in slow motion. The individual crystals within the ice deform and slide past each other, allowing entire masses of ice to creep downhill. This incredible movement gives glaciers their fluid grace, their ability to carve mountains and shape valleys over tens of thousands of years. Under the right conditions, even seemingly solid rock can behave this way, flowing over immense geological timescales. Watching ice deform under pressure in laboratory experiments reveals how matter can blur the line between what we consider solid and what we consider liquid. What appears unyielding to us becomes supple and pliable with enough time and immense weight. The planet's greatest transformations often happen not in sudden bursts of energy, but through the quiet, relentless persistence of materials learning to move under pressure. Sometimes, the smallest, most delicate traces of the past can survive in stone. On slabs of ancient sedimentary rock, scientists have discovered delicate impressions of raindrops that fell onto soft mud hundreds of millions of years ago, long before humans existed. Each tiny crater records a specific moment in time. It's a snapshot of a storm that passed across a primeval landscape, its droplets scattering across a world filled with strange, early plants and primitive life forms. Within seconds, these delicate marks were buried by new layers of sediment, sealing them in darkness until the rock eventually hardened. When the surface is exposed again, it reveals a perfect imprint of weather from a vanished age. These fossilized raindrops remind us that even fleeting moments can last forever when preserved by pure chance. In a single stone, we can read the touch of a storm that ended countless millions of years ago. Its rhythmic pattern is still visible on the silent pages of the planet's memory. For centuries, people thought fossils could only capture bones and shells, the hard parts of ancient creatures. But discoveries over the last few decades have revealed something truly astonishing. Under extremely rare conditions, even delicate soft tissues can survive the fossilization process. In certain types of rock, scientists have found impressions of skin, muscle, and even feathers. Sometimes, there are even traces of pigment, showing the original colors of long, extinct dinosaurs and ancient birds. These incredible fossils form when mineral-rich water seeps through the remains before decay can destroy them, slowly replacing organic molecules with stone. The result is a moment of ancient life perfectly turned into sculpture, preserved in astonishing detail. Some of these fossils even retain microscopic structures that hint at how these creatures moved, how they breathed, and how they shone in the sunlight of their time. To hold such a fossil is to bridge entire worlds, feeling the echo of warmth and color from beings that vanished hundreds of millions of years ago. Long before animals or even plants evolved, simple microbes built layered structures in shallow seas. These formations, called stromatolites, are the planet's oldest known living fossils. They were created by vast mats of bacteria that trapped and bound sediment, forming dome-shaped structures that slowly grew upward towards the sunlight. Some ancient examples of stromatolites are more than 3.5 billion years old, making them among the earliest undeniable evidence of life anywhere on Earth. Remarkably, stromatolites still exist today in a few remote places, such as Shark Bay in Australia, where microbial communities continue their slow, rhythmic growth. Looking at one is like peering directly into the very dawn of biology, to a time when the first cells began shaping the planet as we know it. They remind us that life's story began not with complex motion or intricate structures, but with incredible patience. Layers of living film slowly turning light, water, and time into the very foundation of everything that followed. Around 700 million years ago, our planet almost completely froze solid. This period is known as Snowball Earth. Ice stretched from pole to equator, sealing the vast oceans under miles of frozen crust and reflecting nearly all sunlight back into space. Scientists believe that a combination of intense volcanic activity, significant changes in atmospheric gases, and shifts in solar energy all combined to trigger this global deep freeze. For millions of years, Earth remained a vast, silent world covered entirely in ice, its surface gleaming brilliant white beneath a dim sun. Yet, life endured. It found refuge in hidden pockets of liquid water beneath the massive glaciers or near active volcanic vents. Eventually, Volcanic eruptions released enough carbon dioxide into the atmosphere to trap heat once again, slowly thawing the planet in a dramatic, world-spanning melt. The return of liquid oceans may have then helped trigger an explosion of complex life forms. Snowball Earth stands as one of the greatest transformations in our planet's history, a near-death and subsequent rebirth, written in the silent records of ice and snow. During the deepest parts of that global freeze, volcanoes never stopped erupting. They continued pumping carbon dioxide into the atmosphere for millions of years. With the vast oceans sealed beneath miles of ice, this gas couldn't dissolve into the water as it normally would. So, it steadily built up in the atmosphere, trapping more and more heat. When the ice finally began to melt, the process accelerated dramatically. Dark, exposed rock absorbed more sunlight, amplifying the warming effect. Within what was, geologically speaking, a blink of an eye, the planet shifted from frozen white to steaming blue, green seas once more. This thawing unleashed immense floods, widespread erosion, and perhaps even chemical changes that nourished early life. In a way, volcanoes may have actually saved the planet. Their quiet, persistent activity beneath the ice kept Earth's climate engine alive. What was once an age of silence became one of rebirth, proving that even in the planet's darkest, coldest moments, fire and renewal were waiting patiently below. The air we breathe today owes its very existence to tiny organisms that lived billions of years ago. These microbes, the ancient ancestors of modern cyanobacteria, thrived in shallow seas. They used sunlight to split water molecules, releasing oxygen as a byproduct. Over immense stretches of time, their waste product completely transformed the planet. At first, the free oxygen reacted with dissolved iron in the oceans, forming vast deposits of rust-colored rock. Only after these minerals were completely saturated with oxygen did the gas begin to fill the atmosphere, slowly turning it into the life-giving mixture we depend on today. This monumental event, known as the Great Oxidation Event, changed everything. It allowed complex cells to evolve and eventually made possible the rise of plants and animals. Every breath you take is, in essence, a gift from those ancient microbes whose simple chemistry turned a barren world into a living one, paving the way for forests, oceans, and all the diverse life that followed. In ancient seabeds all around the world, there lie bands of red and gray rock that shimmer with a metallic luster. These banded iron formations are the fossilized record of the precise time when oxygen first appeared in Earth's atmosphere. As primitive microbes began producing oxygen through photosynthesis, the gas reacted with dissolved iron in the oceans, creating rust-like minerals that settled to the seafloor in distinct layers. Over millions of years, these sediments hardened into rock, capturing the very breath of a newly awakening planet. Today, those same formations are mined for iron, which forms the backbone of modern industry. Yet, they began as the byproduct of microscopic life. Each stripe in the stone is like a heartbeat in the planet's grand transformation, marking the slow, steady transition from a world without air to one alive with oxygen, where the chemistry of life itself began to take hold across land and sea. Before oxygen filled the air, Earth's oceans looked very different indeed. The water may have shimmered with captivating shades of red and violet, colored by ancient microbes that used molecules of sulfur, not oxygen, to capture sunlight. These unique organisms thrived in chemical, rich seas under what was likely an orange-hued sky, producing pigments that tinted the water with these strange, vibrant colors. As photosynthetic bacteria began to release oxygen, these purple oceans slowly faded to the familiar blue we know today. The shift from a sulfur-dominated world to an oxygen-rich one was one of the greatest transitions in Earth's long history, altering everything from the atmosphere's composition to the very chemistry of rocks. For a time, though, our planet glowed in colors we can scarcely imagine. Seas of violet beneath a dim sun, a silent signature of early life experimenting with light. Long before the age of vast forests, intricate coral reefs, or any creature that breathed air. The continents we see today are only the latest version of Earth's ever-changing face. In the immense stretches of deep time, entire mountain ranges have risen and then eroded away so completely that almost no trace of them remains. Wind, water, and gravity work with incredible patience, steadily wearing down even the tallest peaks, grain by tiny grain. The ancient roots of these vanished mountains sometimes survive as crystalline rock, buried deep beneath newer layers. These are subtle clues left behind for geologists to find and interpret. Some of the oldest continental crusts once bore enormous mountain ranges, now reduced to flat plains. Over hundreds of millions of years, erosion can erase a mountain as easily as waves smooth a pebble on a beach. The planet is always rebuilding itself, and what seems eternal to us is merely a temporary sculpture in the ongoing, dynamic art of geology. Every plain and every valley was once a towering summit, and every stone carries the ghost of a vanished mountain in its silent heart. Over the course of billions of years, the continents have gathered together and then drifted apart, much like slow, moving pieces of a colossal puzzle. Driven by heat rising from deep within the mantle, the Earth's crust has folded, fractured, and rearranged itself again and again. Each massive collision between continents built new mountain ranges. Each separation opened up new oceans. This incredible process, known as the supercontinent cycle, has repeated at least half a dozen times throughout Earth's history. When continents collide, rocks are buried deep, and then reborn through intense heat and pressure. When they separate, new crust forms, sometimes carrying ancient fragments of lost worlds. The silent scars of these vast migrations are visible today in matching fossils and rock patterns found on opposite sides of modern oceans. The land beneath our feet is not fixed in place, but is part of a grand, restless dance that never truly ends. It's proof that the ground we stand on has traveled immensely far, carrying the history of countless ancient worlds within its very foundations. Before the familiar supercontinent of Pangaea, and even before Rodinia, the Earth's landmasses assembled and broke apart at least 6 times. They formed vast supercontinents that drifted through the ages. Each one of these had its own unique mountains, its own oceans, and its own climates. Each had its own rise and fall, a story written in stone. Nuna, Columbia, Rodinia, Panotia, and Gondwana are some of the names given to these lost worlds. Their remains now scattered across the globe. When they existed, life was often microscopic, but their formation and breakup profoundly shaped the chemistry of the oceans and the atmosphere. Each cycle of breakup and reunion altered the course of evolution, stirring the climate and shifting the deep currents of the planet. The continents we know today are merely pieces of those ancient giants, survivors of a cycle that spans billions of years. To study them is to read Earth's autobiography, written across immense spans of time, where even the land itself is temporary and nothing stays whole for long. Pangaea was only the most recent supercontinent. About 250 million years ago, nearly all the land on Earth gathered into a single, vast supercontinent, surrounded by one enormous global ocean. This colossal landmass, known as Pangaea, stretched from pole to pole, connecting regions that are now continents apart. Its interior was harsh and dry, far from the sea's moderating influence, while its coasts teemed with early reptiles and ancient forests. Over tens of millions of years, heat building up beneath the crust created immense pressure until deep cracks appeared, slowly splitting the land apart. The Atlantic Ocean began to open, and the continents started their gradual drift toward their modern positions. Fossils of identical plants and animals found on opposite sides of the Atlantic Ocean are silent, undeniable witnesses to that ancient unity. Pangaea's breakup shaped modern geography and climate, setting the stage for everything that followed. It was not the first supercontinent, nor will it be the last, only one incredible chapter in Earth's endless drift. The next supercontinent may already be forming, slowly, under the Pacific Ocean. Far beneath the waves, the slow, relentless movements of the tectonic plates are setting the stage for the next great rearrangement of Earth's surface. Scientists predict that in another 200 to 300 million years, the continents may once again converge into a new supercontinent. Some models suggest that the Pacific Ocean will slowly close as Asia and the Americas move together, forming a vast new landmass, sometimes called Amasia. Other models imagine the Atlantic Ocean closing instead, drawing Europe and the Americas toward each other. Though the precise outcome is uncertain, the underlying process is absolutely inevitable. The same invisible currents that tore Pangaea apart are still at work, shifting continents inch by patient inch. To imagine the world that far ahead into the future is to truly realize how temporary and fleeting our current maps really are. The Earth is always remaking itself, and somewhere deep below, the first subtle motions of the next supercontinent have already begun. Australia is steadily drifting north toward Asia, every single year. Far beneath the continent of Australia, the immense tectonic plate that carries it is slowly gliding northward at a pace of a few centimeters each year. Over millions of years, this seemingly gentle motion adds up to thousands of kilometers. Eventually, Australia will collide with the islands of Southeast Asia, raising new mountain ranges and reshaping coastlines dramatically. Satellite measurements already track this yearly drift with astonishing precision. The motion is powered by deep convection currents in the mantle, where heat from the planet's core moves vast sheets of rock as if they were rafts on a molten sea. Though the movement is imperceptible to us in our daily lives, it fundamentally changes maps, climates, and even entire ecosystems. Coral reefs grow where land once lay. Deserts slowly inch toward the tropics. And someday, new mountain ranges will rise between the two regions. The continent's slow, northern voyage is one of the most graceful and powerful migrations on Earth. Africa may one day split into two separate continents. Deep within East Africa, a great rift stretches for thousands of kilometers, clearly marking the place where the continent is slowly tearing apart. Intense volcanic activity, frequent earthquakes, and a noticeably thinning crust all reveal that a new ocean may eventually form there. The East African Rift is a visible reminder that continents are never truly solid or fixed. They bend and stretch like skin over a living body. In a few tens of millions of years, the region that includes Ethiopia, Kenya, and Tanzania could completely separate from the rest of Africa, drifting eastward to become its own distinct landmass. Large lakes, such as Lake Tanganyika and Lake Malawi, fill the rift's deep scars, serving as early clues to the vast ocean that will someday flood in. Standing on its edges is like glimpsing the very birth of a future continent. The entire process is slow beyond human imagination, yet it is happening right now, beneath our feet, quietly shaping the world of tomorrow. The island of Iceland sits directly above a tear in Earth's crust. Iceland exists precisely because it straddles the mid-Atlantic ridge, a boundary where two immense tectonic plates are actively moving apart from each other. Here, molten rock from deep within the Earth wells upward through a long, continuous tear in the crust, constantly building new land as it cools and solidifies. The entire island is a fascinating crossroads of fire and ice, with massive glaciers resting right beside active volcanoes. Hot springs, dramatic geysers, and vast lava fields all testify to the restless, immense energy below. Every few years, volcanic eruptions remind residents that their homeland is still very much under construction. The island's unique position makes it one of the very few places where this crucial plate boundary rises above sea level, allowing scientists to study the raw, fundamental mechanics of plate tectonics in plain view. Iceland is a living experiment of creation, a place where the Earth literally grows before our eyes, balancing precariously on the edge between the frozen North Atlantic and the molten heart of the planet. The Hawaiian Islands are a moving chain, built by a stationary hotspot. In the middle of the vast Pacific Ocean, a persistent plume of molten rock rises from deep within the mantle. This plume punches through the Earth's crust, creating powerful volcanoes. As the Pacific plate slowly drifts northwestward, each new eruption forms an island. This island then eventually moves away from the stationary hotspot, allowing another island to take its place. This continuous process has created a long chain of islands and undersea mountains, stretching thousands of kilometers across the ocean floor. The youngest island, Hawaii, still glows with active lava flows, while the oldest islands, far to the northwest, have eroded into low atolls and submerged seamounts. By carefully tracing this chain, scientists can precisely map the movement of the Pacific plate over millions of years. The hotspot itself remains fixed, while the surface of the Earth glides above it, leaving a dotted, geological record of time and motion. Each island in the chain is a chapter in an ongoing story of creation, written in molten stone. Yellowstone National Park hides one of the largest volcanic systems on Earth. Beneath its famous forests and dramatic geysers lies an immense reservoir of magma, large enough to fuel one of the most powerful volcanic systems ever discovered. The park's steaming vents, bubbling pools of mud, and spectacular eruptions of boiling water are all surface clues to the immense heat and pressure below. Scientists monitor the region incredibly closely, mapping the hidden chambers that stretch for dozens of kilometers beneath the crust. Although it is not expected to erupt anytime soon in a catastrophic way, its past explosions reshaped much of North America, scattering ash across entire continents. Today, the region breathes through its geysers and hot springs, releasing pressure in spectacular bursts that remind us of its inner fire. Yellowstone is both a sanctuary of breathtaking natural beauty and a powerful window into the restless, dynamic nature of the planet, where even beneath tranquil landscapes, ancient forces of heat and pressure continue to shape the Earth in profound silence. When ordinary volcanoes erupt, they might affect local weather for a few seasons. But when supervolcanoes erupt, they can completely transform the entire planet. These titanic explosions release thousands of cubic kilometers of ash and gas into the atmosphere, blocking sunlight and cooling the globe for decades or even centuries. Evidence of such enormous eruptions appears in distinctive ash layers and ancient climate records from places like Yellowstone, Toba, and Taupo. The aftermath of these events includes volcanic winters, where global temperatures drop significantly and ecosystems struggle immensely to adapt. Though incredibly rare, these events remind us of the delicate balance between Earth's interior and its surface. The immense power locked beneath our feet has shaped evolution itself, sometimes triggering mass extinctions that cleared the way for new forms of life. Yet, even in their fury, supervolcanoes are part of the planet's long, rhythmic cycle of renewal, constantly cycling materials between the crust and atmosphere, reminding us that life and fire are deeply and intricately intertwined. The largest known volcanic eruption in recorded geological history happened in what is now Indonesia. Around 74,000 years ago, a colossal eruption at Lake Toba in Indonesia fundamentally changed the world. It expelled more than 2,000 cubic kilometers of ash and magma, leaving behind a massive caldera 100 kilometers wide that is still clearly visible today. The blast darkened skies across the entire globe, significantly lowering global temperatures and spreading volcanic ash over multiple continents. Some scientists believe it caused a brief but severe volcanic winter that may have significantly influenced early human populations. Even after the eruption itself ended, volcanic gases lingered in the atmosphere, tinting sunsets with dramatic colors and cooling the planet for years afterward. The event was so vast that it dwarfs any eruption in recorded human history. Today, the tranquil lake that fills the caldera seems peaceful and calm. But beneath its calm waters lies one of Earth's most powerful scars, a silent reminder that the planet's greatest moments of creation often come wrapped in immense destruction. Fine volcanic ash can drift in the upper atmosphere for years after a major eruption. It's carried by powerful winds that circle the entire planet. Tiny particles from major eruptions, such as Mount Pinatubo in the Philippines or Krakatau in Indonesia, have been detected long after the initial explosions ended. These microscopic fragments scatter sunlight, producing brilliant red sunsets and slightly cooling global temperatures. High above the weather systems we experience, they form thin, almost invisible veils that reflect light in ways that painters once captured after historic eruptions. Some layers of airborne ash even return to Earth centuries later, discovered perfectly preserved in ice cores and ocean sediments. Every eruption, no matter how remote, connects to the single atmosphere that wraps the entire planet. The very air we breathe today carries faint traces of eruptions from distant ages, a delicate reminder that even the calmest sky holds quiet echoes of the Earth's fiery breath. In a few rare volcanic craters around the world, molten rock never completely solidifies. These are known as lava lakes, such as those found in Erdeal in Ethiopia and Kilauea in Hawaii. They are sustained by constant supplies of heat and fresh magma from deep below. Their surfaces churn and ripple like fiery oceans, often crusting over with a thin layer of solid rock, only for it to break apart again. At night, they glow with an intense orange light. Like windows into the planet's very heart, their light flickering against the dark rock and rising smoke. The heat balance is so incredibly precise that these lakes can persist for decades, continuously refreshed by deep circulation of magma. Watching one is truly mesmerizing, like observing a living furnace, breathing and pulsing in a slow, powerful rhythm. They offer scientists rare and invaluable insights into the chemistry and physics of magma that cannot be replicated in laboratories. Each lava lake is a powerful reminder that the Earth's fire still burns just beneath its thin, cooling crust, timeless and eternally alive. When a volcano erupts, the immense friction between ash particles creates powerful electrical charges. As these charges build up, they discharge as dramatic lightning bolts that crackle and flash through the ash plume. Volcanic lightning can illuminate entire skies, creating spectacular storms of fire and light above erupting mountains. Unlike ordinary thunderstorms, these flashes are born entirely from the raw energy of rock and gas being violently ejected. Photographs capture branching bolts of lightning, arcing dramatically through towering columns of black smoke, each strike lasting only a heartbeat, but carrying immense power. Scientists study these flashes to understand the flow of ash and to track the intensity of the eruption, since the frequency and strength of lightning can signal how violently material is being ejected. To witness one is to see the fusion of Earth's most elemental forces, solid rock, liquid magma, and gas meeting electricity. It's a brief, awe-inspiring display that reveals how even destruction can shimmer with extraordinary beauty. In places where massive glaciers rest atop active volcanoes, heat and ice collide in spectacular and often explosive ways. When magma rises beneath the ice, it melts huge volumes of water almost instantly, producing steam that expands with incredible explosive force. These eruptions can blast straight through the glacier, sending immense floods and ash clouds cascading down valleys. Iceland's volcanoes often behave this way, hidden beneath thick ice caps until the pressure builds high enough to burst free. The interaction leaves behind unique landforms, distinct ridges and plateaus sculpted by fire and water working together. Scientists call them toyas, monuments to the strange and powerful partnership of intense heat and extreme cold. Each eruption beneath ice rewrites the landscape, proving that even the most opposite elements of nature are connected in a profound cycle of creation and transformation that has shaped our planet since its earliest days. Across the oceans, new land sometimes appears where there was once only water. Submarine volcanoes occasionally erupt with such immense force that they build entire islands from the seafloor upward. In the past century, eruptions near Iceland, Japan, and Tonga have created fresh patches of land that still steam and harden under the sun. Some of these newborn islands vanish again within years, slowly eroded by waves, while others grow stable enough to host life. These newly emerged islands reveal the planet's creative power unfolding in real time. To watch one form is to witness the very process that built entire continents long ago. Birds, plants, and eventually even humans find their way there, slowly turning raw lava into complex ecosystems. The emergence of new islands reminds us that Earth is not finished with its work. The planet continues to build, break down, and begin again, renewing its surface one dramatic eruption at a time. In parts of Africa, certain deep lakes contain massive amounts of dissolved carbon dioxide trapped beneath their surfaces. When the delicate balance of temperature or pressure changes suddenly, that gas can burst upward in a deadly, invisible wave. Lake Nyos in Cameroon released such a cloud in the 1980s, tragically suffocating life in nearby valleys. Scientists now monitor these lakes incredibly carefully and have installed systems to safely release gas before pressure builds too high. This phenomenon is called a limnic eruption, a rare but incredibly powerful reminder of how even tranquil waters can conceal immense, hidden energy. The gas originates from volcanic sources below the lake bed, slowly seeping upward through cracks in the crust. Over centuries, it dissolves into the water, much like carbonation in a sealed bottle of soda. When it finally escapes, the result is silent and shocking, a natural event as strange as it is terrifying. Beneath many cities and fields, hidden cavities form where limestone or salt slowly dissolves in underground water. When the roof of one of these voids collapses, the ground above can suddenly drop away, creating a sinkhole. Some are only a few meters wide, while others can stretch hundreds of meters across, devouring cars, trees, and even homes without warning. They form most often after heavy rain, when water seeps through cracks and further weakens the layers below. Entire neighborhoods have sometimes been built atop such fragile foundations without anyone realizing it. Scientists now map vulnerable regions with radar and ground sensors to detect these hidden cavities before disaster strikes. Though dramatic and often destructive, sinkholes are part of the planet's natural recycling of rock, where water patiently sculpts the landscape from beneath. Each collapse reveals the fragile balance between solid ground and the hidden hollows that lie quietly just below our everyday world. Where limestone or dolomite dominates the bedrock, rainwater slowly carves intricate networks of tunnels and vast caverns. These underground systems can stretch for hundreds of kilometers, carrying entire rivers beneath the surface. The land above sometimes collapses in places, forming the sinkholes, valleys, and jagged ridges characteristic of what is called karst terrain. Water disappearing into a cave entrance might emerge miles away as a clear, bubbling spring. In some regions, entire ecosystems have adapted to these lightless waterways, from blind fish to translucent insects. Karst landscapes are found on every continent and provide drinking water for millions of people. Yet, their hidden, intricate nature makes them incredibly vulnerable to pollution. Exploring them is like entering the circulatory system of the planet, where stone and water move together in an endless dialogue, dissolving, shaping, and renewing the surface of the earth, drop by patient drop. Inside limestone caves, dripping water carries dissolved minerals that slowly crystallize as the water evaporates. From the ceiling, each tiny droplet leaves behind a microscopic ring of calcite that lengthens downward over centuries, forming what we call a stalactite. Where these drops land on the cave floor, matching mounds grow upward as stalagmites. Eventually, over immense spans of time, they can meet to create towering columns that seem to hold the entire cave aloft. The process is so incredibly gradual that growth rates are measured in millimeters per century. A lantern's light reveals their delicate, intricate textures, like frozen waterfalls sculpted by time and immense patience. These formations are living records of the cave's history, quietly recording changes in water chemistry and climate. When viewed together, they resemble vast forests of stone, where every delicate branch and sturdy trunk was born from a single droplet that fell through darkness, carrying the ancient memory of rain and the passage of unthinkable time. The breathtaking shapes and formations found inside caves are products of unimaginable patience. Stalactites, flowstones, and crystal draperies accumulate one microscopic layer at a time as water leaves behind thin films of mineral. A single centimeter of growth can take hundreds of years. The precise rate depends on the consistency of the water drip, the purity of the dissolved minerals, and even the temperature of the surrounding rock. Some formations still glisten, wet from drops that began their long journey through the ground decades ago. Studying their intricate layers allows scientists to reconstruct past climates, revealing ancient droughts, immense floods, and significant shifts in rainfall patterns long before any written human history. Walking through a cavern is like entering a slow motion clock, where time moves at the deliberate pace of minerals crystallizing. These subterranean sculptures remind us that beauty can emerge not from speed or brute force, but from stillness and persistence far beyond human measure. Deep underground, large cave networks can develop their own distinct microclimates, completely different from the surface. Temperature, humidity, and airflow combine to create fogs, winds, and even tiny clouds that drift through the chambers. Warm air rising from deeper passages meets cooler air near entrances, producing swirling currents that resemble miniature weather fronts. Some caves experience regular breathing, exhaling warm air in winter and inhaling cool air in summer as outside conditions change. This unique environment causes moisture to condense on walls, dripping to sustain delicate formations and unique ecosystems. To step inside is to feel the planet itself inhale and exhale, the rhythm of air and rock joined together in a slow, ancient dance. These hidden climates preserve fossils, ancient artifacts, and unique species that cannot survive anywhere else. Within their stone lungs, caves remind us that even the most solid parts of Earth are filled with subtle movement, gentle breath, and intricate patterns of a living atmosphere. Beneath the rolling hills of Kentucky lies Mammoth Cave, the largest known cave system on Earth. Its passages extend for more than 400 miles, and new tunnels are still being discovered by explorers. This vast network was carved by ancient rivers, dissolving limestone over millions of years, branching and looping in a labyrinth that could easily hide entire cities within its immense depths. Explorers move through narrow crawls, towering chambers, and underground rivers that still reshape the rock today. The air inside remains consistently cool and still, and the silence is so profound, it seems almost alive. The cave's sheer vastness challenges the imagination, reminding visitors how much of the planet exists unseen beneath our feet. Mammoth Cave is both a geological wonder and a living record of time, carved by water's quiet persistence into a cathedral of stone that stretches into darkness without apparent end. When a massive earthquake shifts the distribution of Earth's mass, the planet's rotation subtly changes. The effect is incredibly tiny, usually measured in microseconds, but it's still measurable by precise instruments. By moving enormous slabs of rock, an earthquake can slightly alter the planet's moment of inertia, much like a spinning ice skater speeds up when they pull their arms inward. After the devastating 2004 Sumatra earthquake, scientists calculated that the day shortened by mere fractions of a second. The event also nudged the precise position of the poles and adjusted the overall shape of the planet ever so slightly. These minute shifts remind us that even the concept of a day, which feels so absolute and unchanging, is influenced by the deep, powerful movements of rock and gravity. Each major earthquake is not only a surface event, but a truly planetary one, echoing through the rotation of the world itself and whispering change into the very rhythm of time. When a powerful earthquake strikes, the immense energy it releases doesn't just stop at the epicenter. Seismic waves ripple outward through the entire planet, racing through solid rock and molten mantle like sound through a giant bell. Sensitive instruments can detect the same quake echoing around the world several times before its energy finally fades away. The largest earthquakes make the entire Earth tremble, subtly flexing its crust as energy moves from one side of the globe to the other. Even regions thousands of kilometers away can feel the faint aftershocks. Scientists use these global reverberations to map the planet's interior, tracing how the waves bend and reflect inside molten layers. Each tremor reveals something crucial about the structure of the deep Earth, where it's solid, where it's fluid, and how heat moves within. Every great earthquake briefly turns the world into a single, vibrating instrument, humming softly with its own powerful heartbeat. The sheer scale of an earthquake's energy is staggering to comprehend. When the largest faults rupture, they can release as much power as several million tons of explosive material detonating all at once. The shaking that we feel on the surface is only a small part of this immense energy. Most of the energy travels deep into the Earth's crust, moving rock layers that weigh more than entire mountain ranges. The moment magnitude scale, which scientists use today, was designed to measure these immense forces much more accurately than older systems. During the 2011 Tohoku earthquake in Japan, the energy released was enough to alter the rotation of the planet and shift the seafloor by several meters. It's difficult to grasp such enormous numbers, but each major earthquake reminds us that the Earth's crust is under constant, immense pressure, always storing and releasing energy in a slow, powerful rhythm that sculpts continents and seas over vast periods of time. Though stone feels incredibly solid and unyielding to us, deep inside the Earth, it behaves very differently. At great depths, where temperatures and pressures rise beyond our imagination, rock begins to deform slowly, flowing like an extremely thick, viscous liquid. Over millions of years, this plastic movement allows entire mountain ranges to rise, fold, and even melt into new formations. Minerals within the rock stretch and twist, creating intricate patterns that can be seen in metamorphic rocks exposed at the surface today. In controlled laboratory experiments, geologists have watched samples of rock bend, rather than break, when heated and compressed, confirming that time itself changes how matter behaves. The mantle beneath our feet constantly moves this way, its slow, persistent flow driving the drifting of continents above. It's a profound reminder that even what seems rigid and unchangeable is capable of motion, and that the true strength of stone lies not only in its hardness, but in its ability to yield, reshape, and ultimately endure. When rocks are buried deep within the Earth's crust, they undergo a profound transformation. Immense heat and pressure reorganize their minerals without melting them entirely, creating entirely new textures and structures. Granite, for example, becomes gneiss. Limestone transforms into marble. Shale becomes slate. Each type of metamorphic rock carries a detailed record of the forces that shaped it, like pages in a geological diary. Scientists can read these ancient records to reconstruct past mountain, building events, or to determine the immense depths at which certain rocks once rested. Some metamorphic formations even reveal the direction of ancient tectonic movement through the precise alignment of their minerals. When uplift eventually exposes them at the surface, we glimpse the planet's internal history, frozen in crystalline form. They are literally stones that remember, preserving within their intricate folds the immense energies that flow invisibly beneath the crust, showing that every mountain once lay hidden, being rewritten by intense heat, crushing pressure, and vast spans of time. Beneath ancient seas, layers of mud once settled in quiet, undisturbed darkness. Over millions of years, these sediments compacted under the immense weight of newer layers above them, squeezing out water and aligning tiny clay minerals into flat, parallel sheets. With further heat and pressure, that mud hardened into slate, a rock so finely layered that it can be easily split into smooth, thin tiles. The transformation is a powerful story of stillness turned to incredible strength, the patience of soft sediment reborn as enduring stone. Slate once formed entire seafloors. Today, it roofs cottages and lines pathways, carrying the silent imprint of ancient oceans into our modern world. If you hold a piece and tilt it to the light, you can still see the subtle sheen of its compressed minerals, tiny echoes of clay that once drifted lazily through ancient water. It's proof that even the softest, most yielding materials can, through time and pressure, become incredibly enduring and strong. Long before it gleamed in grand temples and magnificent sculptures, marble began its life as humble limestone on the seafloor. That original limestone was composed of the shells and skeletons of countless marine creatures, corals, plankton, and mollusks, all compacted over millions of years. When this limestone was buried deep within the earth, it met intense heat and pressure that caused its crystals to grow and recrystallize. This process erased visible fossils and created the smooth, interlocking texture of marble. Trace minerals incorporated during this transformation added subtle, beautiful colors: iron for reds, serpentine for greens, graphite for grays. When polished, these minerals catch the light, giving marble its famous, almost luminous glow. Ancient civilizations prized it because it seemed to hold sunlight within its depths. In truth, it is a magnificent relic of vanished oceans, born from life, death, and profound geological transformation. Every polished surface of marble, from a towering cathedral column to a delicately carved statue, was once part of a living sea that eventually hardened into timeless beauty. Every single gemstone tells the unique story of its geological birth. Hidden deep in the Earth's crust, immense heat, crushing pressure, and intricate chemistry collaborate to create crystals of astonishing beauty. Diamonds form under incredible crushing forces hundreds of kilometers down, while emeralds grow in mineral, rich veins where water and rock patiently exchange elements. Rubies, sapphires, topaz, and quartz each arise from precise conditions of temperature and chemistry that rarely coincide. That rarity is precisely what makes them so precious. When cut and polished, their clarity and brilliance reveal the harmony of their atomic structures, offering a glimpse into perfect order forged in chaos. Gemstones travel from deep within the rock to human hands, carried through volcanoes, erosion, and vast spans of time. Each one is a silent messenger from a different, unique environment within the planet, a beautiful record of its hidden processes. To look deeply into a gemstone is to peer backward into the Earth's memory, seeing the patience of pressure and the exquisite art of crystallization, written in perfect, glittering symmetry. At first glance, rubies and sapphires appear to be completely different stones, but both are actually varieties of the very same mineral, corundum. In its pure form, corundum is colorless, composed of aluminum and oxygen atoms arranged in a tightly packed crystalline lattice. When tiny amounts of chromium elements enter that structure, it glows a brilliant red and becomes a ruby. When iron and titanium elements take its place, the result is a beautiful blue sapphire. Other trace elements can produce yellows, greens, or even pinks. These subtle substitutions in the atomic makeup of the crystal change the way light passes through it, giving each gem its distinct and vibrant hue. The fact that two of the world's most prized and distinct stones come from the same basic mineral shows how small changes at the atomic level can yield astonishing beauty and variety. Every color is a precise fingerprint of chemistry, powerful proof that nature's artistry begins in the invisible, intricate dance of elements deep within the earth. Among gemstones, emeralds are among the most elusive and rare. They require a perfect meeting of two very different worlds, silica-rich rocks and beryllium-bearing fluids. These are conditions that rarely, if ever, coincide in nature. When they do, the mineral beryl forms, colored a vibrant green by tiny traces of chromium or vanadium. This delicate balance occurs only in certain mountain regions where intense tectonic activity has thoroughly blended these specific ingredients. The result is a gem that carries the tension and improbable nature of its birth within every shimmering facet. Most emeralds contain tiny fractures and inclusions, often called jardins or gardens, that mark their natural formation. These imperfections are not flaws, but rather signatures of authenticity, powerful evidence that the stone is a true child of the earth. To hold one is to hold the incredible story of improbable chemistry, immense pressure, and geological patience that conspired to create something impossibly rare and luminous. Opal is unlike most gemstones because it isn't crystalline in structure. It forms when water-carrying dissolved silica trickles slowly through rock, depositing microscopic spheres that stack in delicate, intricate layers. These spheres then scatter light, producing opal's characteristic rainbow shimmer, known as play of color. Many opal deposits began in arid landscapes that were once wet millions of years ago. As the water slowly evaporated, it left behind these intricate, glowing structures. Under magnification, opal reveals a hidden world of order within apparent chaos, a natural mosaic of colors suspended forever in stone. Australia, home to some of the world's finest specimens, was once part of an ancient inland sea where these precise processes unfolded. Every opal captures not only the light we see, but also the memory of vanished rain, lost rivers, and the quiet chemistry that turns water and sand into fire, frozen forever in stone. When fragments of rock fall from space, they bring messages from the very earliest days of our solar system. Meteorites on Earth tell stories from before our planet was even born. Some meteorites formed billions of years ago, long before Earth itself existed, from the same vast cloud of dust and gas that gave birth to our Sun and all the planets. They contain minerals that have remained utterly unchanged since that time, perfectly preserving a record of ancient chemistry. Scientists painstakingly study them to learn how the fundamental building blocks of planets assembled, melted, and differentiated into distinct cores and crusts. Some even carry organic compounds, subtly hinting that the essential ingredients for life were scattered through space long before Earth ever began to form. To hold a meteorite in your hand is to literally touch something older than our world itself. It's a piece of cosmic debris that has traveled across unimaginable stretches of time and distance to finally rest in our hands, carrying the silent memory of creation itself. Within certain meteorites, scientists have discovered microscopic grains called pre-solar dust. These are actual remnants of ancient stars that existed even before our Sun. some rocks are literally older than the solar system itself. These tiny crystals formed in the outer layers of dying stars and were then carried into space by powerful stellar winds. Over billions of years, they drifted through the galaxy, eventually becoming trapped in the vast material that built our solar system. Their unique isotopic fingerprints clearly reveal their alien origins, differing from anything found naturally on Earth. To find such grains inside a rock is to discover actual stardust, untouched by planetary processes, matter that truly predates the world itself. When we meticulously analyze these tiny particles, we read stories written before the sun ever rose, the faint echoes of supernovas, and the slow, rhythmic breath of red giants. Each grain is a whisper from the galaxy's deep past, powerful proof that the Earth itself was born from recycled stars. The samples collected from the Moon during the Apollo missions did more than just reveal lunar history. Lunar rocks, brought back by astronauts, helped date Earth's early crust. They unlocked crucial secrets about Earth's own beginnings. The isotopic composition of lunar rocks precisely matches that of Earth's mantle, strongly supporting the theory that the Moon formed from debris left behind after a colossal collision between a young Earth and another planet-sized body. By studying those rocks, scientists could accurately estimate when Earth's crust first solidified, around 4.5 billion years ago. Some of the oldest lunar basalts also record immense impacts that shaped the early solar system. Their surfaces, pitted by countless micrometeorites, have remained unchanged for eons, perfectly preserving a record of ancient bombardment that has been largely lost on our own eroded planet. Every moon rock brought home is a priceless time capsule, connecting two worlds forever linked by a single, violent origin story, written in dust and fire. Analysis of those ancient zircons revealed chemical ratios consistent with rocks that had clearly interacted with liquid water. These zircons record the first liquid water on Earth. That remarkable discovery pushed the timeline for Earth's oceans far earlier than once thought, suggesting that liquid water existed perhaps within 200 million years of the planet's formation. Before this finding, scientists generally believed the young Earth was a molten, fiery sphere for hundreds of millions of years. The zircons, however, showed that the surface had cooled enough to sustain rain, rivers, and oceans surprisingly soon after its birth. This realization completely reshaped our understanding of planetary habitability, suggesting that conditions suitable for life appeared much more quickly than previously imagined. Each zircon, smaller than a grain of sand, is a microscopic archive of water's arrival on Earth. Through them, we glimpse a world where vapor condensed, clouds formed, and the very first drops of rain fell upon cooling rock. It was the beginning of the blue planet we know today. Throughout deep time, enormous volcanic events, known as flood basalt eruptions, blanketed vast regions of the Earth in thick sheets of molten rock. The continents were once covered in lava fields the size of entire countries. These outpourings sometimes continued for millions of years, forming plateaus thousands of meters thick and covering areas larger than modern nations. The Deccan Traps in India and the Siberian Traps in Russia are two dramatic examples of such ancient events. Such eruptions released immense volumes of gas into the atmosphere, drastically altering global climate and ecosystems. When they eventually cooled, they left behind distinctive landscapes of stepped rock and incredibly rich soils that still shape agriculture today. Standing atop one of these regions is to stand upon frozen lava that once flowed in colossal rivers of fire, literally rewriting continents. These vast fields of basalt remind us that the Earth's calm present hides a fiery, turbulent past, when entire regions pulsed with magma and the very air shimmered with volcanic light. The largest volcanic outpourings didn't just reshape continents, they profoundly reshaped life itself. Those lava floods have caused mass extinctions in the past. The gases and ash released during flood basalt events could poison the air, darken skies globally, and disrupt climate for thousands of years. The Siberian Traps eruption, occurring around 250 million years ago, coincided precisely with the greatest extinction in Earth's history, wiping out most marine species and many on land. These catastrophic releases of carbon dioxide and sulfur dioxide triggered acid rain and severe global warming, unraveling entire ecosystems. Yet, in the aftermath, new life eventually flourished, adapting to the drastically changed world. These cycles of destruction and renewal are intricately woven into Earth's long story, powerful reminders that even the most devastating events become part of the foundation for what comes next. In every extinction event lies the seed of evolution, a silent transformation written in ash and stone. Across the world, thin, subtle layers of volcanic ash are preserved within sediment and soil. Ash from ancient eruptions still lies buried in modern soils. These are silent records of eruptions that occurred thousands or even millions of years ago. Each layer can be meticulously traced to its source volcano by the unique chemical signature of its minerals, allowing scientists to match distant sites and build precise timelines of past events. Farmers sometimes unknowingly work these ancient ashes into their fields, their rich minerals enriching the soil with vital nutrients. In places like Italy, Iceland, and Japan, volcanic deposits have made the land extraordinarily fertile. To dig into such soil is to literally touch history, the residue of fire transformed into life. The same ash that once blotted out the sun now nourishes crops and forests, completing a cycle where destruction feeds creation, and the remnants of catastrophe sustain the quiet persistence of growth. Before the vast ocean we know today existed, the land that became Africa and the Americas was joined in a single supercontinent. The Atlantic Ocean was once just a long rift valley. Deep cracks began to open between them around 200 million years ago, forming a vast rift that slowly filled with water as the continents drifted farther and farther apart. Over millions of years, continuous volcanic activity widened the gap, and a brand new ocean was born. The Mid-Atlantic Ridge, where new crust still forms today, marks the original line of separation. Ancient rift valleys, like the one actively forming in East Africa, offer fascinating glimpses of what the early Atlantic once looked like: long depressions, scarred by fault lines, and filled with rising magma. What is now an immense ocean began as a mere fracture in the Earth's crust, powerful proof that even vast seas start as narrow wounds in stone that slowly deepen until they become entire worlds of their own. In the heart of the Atlantic Ocean lies a colossal mountain range hidden beneath the waves. The sea spreads outward from the Mid-Atlantic Ridge like a conveyor belt. Here, new crust is continuously formed. Magma rises through deep cracks, cools, and pushes older rock aside in a steady, symmetrical flow. As this happens, the continents on either side drift farther and farther apart, carried by the very movement of the seafloor itself. Magnetic minerals within the cooling lava align with the direction of the planet's magnetic field, creating distinctive striped patterns that record ancient magnetic field reversals. By meticulously measuring these stripes, scientists confirmed that the seafloor truly spreads, definitively validating the theory of plate tectonics. The process continues at a rate of a few centimeters per year, imperceptible yet absolutely unstoppable. This underwater conveyor of creation constantly expands the ocean, even as old crust is pulled downward at subduction zones elsewhere, keeping the surface of the Earth in constant, living motion. Deep beneath the ocean surface, along the vast ridges where tectonic plates meet, seawater slowly seeps into the crust through cracks and fissures. Hydrothermal vents create black smokers on the ocean floor. It descends until it touches molten rock, heating to hundreds of degrees before rising again, laden with dissolved metals and minerals. When that superheated water bursts back into the cold ocean, it cools instantly, precipitating clouds of dark material that billow upward like smoke. These, black smokers, are underwater chimneys made of mineral and heat, continuously forming and collapsing. They build mounds of iron, sulfur, and other compounds that shimmer faintly in the deep. Around them, the water often glows faintly from reflected particles, and a strange form of life thrives, feeding not on sunlight, but on chemistry. Each vent is a miniature world, a living reminder that even in eternal darkness, the planet finds ways to breathe, burn, and build. Far from the reach of sunlight, life gathers around deep, sea hydrothermal vents in dense, thriving colonies. Those vents support entire ecosystems without sunlight. Here, instead of photosynthesis, organisms rely on chemosynthesis, a process where bacteria use chemical energy from sulfur and methane to produce food. Giant tube worms, clams, crabs, and fish all depend on these microscopic producers, forming ecosystems unlike any other on Earth. Temperatures near the vents can swing dramatically from near freezing to over 300 degrees Celsius within mere meters. Yet, life not only survives, but thrives in these extreme conditions. The discovery of these ecosystems in the 1970s completely changed our understanding of biology forever, revealing that life does not require sunlight, only energy and water. Scientists now suspect similar environments could exist on icy moons like Europa and Enceladus. The dark ocean floor, once thought to be barren, hums with life powered by the planet's internal heat, a profound partnership between geology and biology still unfolding. At hydrothermal vent sites, minerals continuously precipitate from the superheated fluids streaming into the ocean. Minerals there build chimneys taller than houses. Over time, they accumulate into towering chimneys that can reach heights of more than 20 meters. These structures grow upward as long as the flow continues, layer upon layer of sulfides and other minerals forming intricate columns that resemble cathedrals in the deep. Some collapse under their own immense weight, only to rebuild again slowly over time. Within these formations, metallic ores concentrate, the very same types humans mine on land. Their shimmering surfaces host entire communities of microorganisms and animals, each perfectly adapted to the searing temperatures and chemical gradients. The vents pulse like underwater volcanoes, their chimneys smoking gently in the dark. They are powerful proof that even in the most extreme environments, the Earth sculpts beauty from pressure and heat, crafting elaborate monuments that few eyes will ever directly see. The planet's magnetic poles have reversed repeatedly throughout its history, swapping north for south hundreds of times. Earth's magnetic field has flipped hundreds of times throughout its history. These flips occur irregularly, sometimes separated by hundreds of thousands of years, other times by millions. The cause lies deep within the molten outer core, where swirling currents of liquid iron generate the magnetic field. As these currents shift, the field weakens, reorganizes, and eventually reverses its polarity. Evidence of this constant flipping is clearly written in volcanic rocks on the seafloor, where iron minerals align with the magnetic field as the lava cools. Each stripe of opposite polarity marks a specific moment in this long, dynamic cycle. Although a reversal could take thousands of years to complete, life has persisted through every single one of them without major disruption. The phenomenon reminds us that even the invisible shield protecting Earth from cosmic radiation is dynamic, a living force shaped by the continuous movement of the planet's molten heart. If you could stand on Earth during a period of magnetic reversal, your compass would slowly begin to misbehave. During those flips, compass needles would have pointed south. Over centuries, magnetic north would drift toward the equator, then beyond it, until it eventually pointed roughly south. These changes unfold gradually as the magnetic field weakens, splits into multiple poles, and finally re-establishes itself in reverse polarity. Rocks preserve the memory of such shifts, their magnetic minerals frozen in the direction that was north at the time of their formation. Studying these ancient orientations has allowed scientists to trace the precise timeline of reversals and the wandering of poles across the planet. Though the idea might seem unsettling, magnetic reversals are natural and have been frequent throughout Earth's long history. They have never caused mass extinctions or atmospheric collapse. Instead, they reveal the vitality of the geodynamo, the deep, unseen engine that keeps the planet's magnetic heart beating across the ages. Even today, the magnetic poles wander by miles each year. The Earth's magnetic field is not fixed firmly in place. The North Magnetic Pole, once located reliably in the Canadian Arctic, is now racing towards Siberia at a remarkable speed of more than 30 kilometers per year. This continuous drift happens because of dynamic changes in the molten iron flowing through the planet's outer core. As convection currents shift, they alter the delicate balance of magnetic forces above. Instruments aboard satellites continuously track the pole's movements, constantly updating navigation systems that rely on their precise position. While the magnetic north wanders, the geographic North Pole remains steady, making the 2 points distinct and separate. To most people, the difference goes unnoticed in daily life. But to scientists, the shifting poles are a powerful reminder that the field protecting our atmosphere is alive and constantly evolving. The same invisible motion that guides compasses also reveals the slow, liquid heartbeat of the world beneath our feet. Without the moon's steadying influence, Earth's tilt could vary wildly over time, swinging from near upright to deeply angled. The moon stabilizes Earth's wobble, which shapes long-term geology. Such instability would cause chaotic climate shifts, turning frozen poles into tropical zones and back again, unpredictably. The moon's gravity, however, keeps the planet's axial tilt stable within a narrow, consistent range. This crucial stability has allowed long-term geological and biological cycles to flourish, providing consistent patterns for ocean currents, ice ages, and global weather systems. The tides created by the moon's gravitational pull also help distribute energy through the vast oceans, influencing erosion and sediment movement along coastlines. Our planet's geological calm, its delicate balance between order and change, owes much to this silent partner orbiting above. Every gentle tide and rhythmic season is, in part, a gift from the moon, which has guided Earth's intricate dance for more than 4 billion years without missing a single turn. Each day, the ocean rises and falls as the moon's gravity tugs at Earth's water. Tides caused by the moon sculpt coastlines across millennia. Over years and centuries, home to some of the finest specimens, was once part of an ancient inland sea where these precise processes unfolded. Every opal captures not only the light we see, but also the memory of vanished rain, lost rivers, and the quiet chemistry that turns water and sand into fire, frozen forever in stone. When fragments of rock fall from space, they bring messages from the earliest days of our solar system. Some meteorites formed billions of years ago, long before Earth even existed, from the same vast cloud of dust and gas that gave birth to our Sun and all the planets. They contain minerals that have remained utterly unchanged since that time, preserving a perfect record of ancient chemistry. Scientists study them to learn how the fundamental building blocks of planets, first assembled, melted, and then differentiated into distinct cores and crusts. Some even carry organic compounds, hinting that the essential ingredients for life were scattered through space long before Earth began to form. To hold a meteorite is to touch something truly older than our world, a piece of cosmic debris that has traveled across unimaginable time and distance to rest in our hands, carrying the silent memory of creation itself. Within certain meteorites, And even within some ancient terrestrial rocks, scientists have discovered microscopic grains called pre-solar dust. These are actual remnants of ancient stars that existed long before our sun was even born. These tiny crystals formed in the outer layers of dying stars and were then carried into space by powerful stellar winds. Over billions of years, they drifted through the galaxy, eventually becoming trapped in the material that built our solar system. Their isotopic fingerprints reveal their alien origins, differing from anything found naturally on Earth. To find such grains inside a rock is to discover stardust untouched by planetary processes, matter that actually predates the world itself. When we analyze these minute particles, we read stories written before the sun ever rose, the echoes of supernovas and the slow, deliberate breath of red giants. Each grain is a whisper from the galaxy's deep past, powerful proof that the Earth itself was born from recycled stars. The samples collected from the Moon during the Apollo missions did more than just reveal lunar history. They unlocked profound secrets about Earth's own beginnings. The isotopic composition of lunar rocks matches that of Earth's mantle, strongly supporting the theory that the Moon formed from debris left behind after a colossal collision between a young Earth and another planet-sized body. By carefully studying those moon rocks, scientists could estimate when Earth's crust first solidified around 4.5 billion years ago. Some of the oldest lunar basalts also record impacts that shaped the early solar system. Their surfaces, pitted by countless micrometeorites, have remained unchanged for eons, preserving a record of ancient bombardment that has long been lost on our eroded planet. Every moon rock brought home is a time capsule, connecting two worlds forever linked by a single, violent origin story, written in dust and fire. In the ancient rocks of Western Australia, geologists discovered microscopic crystals of zircon that date back more than 4 billion years. These incredibly resilient minerals formed very soon after the Earth itself, surviving countless cycles of erosion and metamorphosis. Inside each one lies a tiny trace of uranium that has slowly decayed into lead, allowing scientists to measure their age with extraordinary precision. The zircon's composition shows that liquid water already existed on the planet when they formed, suggesting that Earth's surface cooled surprisingly quickly after its violent birth. They are among the few surviving witnesses of the planet's earliest chapter, fragments that outlasted the destruction of entire continents. To hold a zircon under a microscope is to look directly into the very dawn of Earth's history, a crystal memory of a time when the world was still forming its oceans, its crust, and its atmosphere. Analysis of those ancient zircons revealed chemical ratios consistent with rocks that had clearly interacted with liquid water. That remarkable discovery pushed the timeline for Earth's oceans far earlier than once thought, perhaps within just 200 million years of the planet's formation. Before this finding, scientists believed the young Earth was a molten sphere for hundreds of millions of years. The zircons showed that the surface had cooled enough to sustain rain, rivers, and oceans surprisingly soon. This realization completely reshaped our understanding of habitability, suggesting that conditions suitable for life appeared much more quickly than previously imagined. Each zircon, smaller than a grain of sand, is a microscopic archive of water's arrival on Earth. Through them, we glimpse a world where vapor condensed, clouds formed, and the first drops of rain fell upon cooling rock. It was the true beginning of the blue planet we know today. Throughout deep time, enormous volcanic events, known as flood basalt eruptions, blanketed vast regions of the Earth in thick sheets of molten rock. These outpourings sometimes continued for millions of years, forming plateaus thousands of meters thick and covering areas larger than modern nations. The Deccan Traps in India and the Siberian Traps in Russia are two dramatic examples. Such eruptions released immense volumes of gas into the atmosphere, drastically altering global climate and ecosystems. When they cooled, they left behind distinctive landscapes of stepped rock and incredibly rich soils that still shape agriculture today. Standing atop one of these regions is to stand upon frozen lava that once flowed in colossal rivers of fire, literally rewriting continents. These vast fields of basalt remind us that the Earth's calm present hides a fiery past, when entire regions pulsed with magma and the air shimmered with volcanic light. The largest volcanic outpourings didn't just reshape continents, they reshaped life itself. The gases and ash released during flood basalt events could poison the air, darken skies, and disrupt climate for thousands of years. The Siberian Traps eruption around 250 million years ago coincided with the greatest extinction in Earth's history, wiping out most marine species and many on land.